Okay, chapter 13. Chapter 13 is equilibrium. Now, we saw equilibrium in chapter 12, and we're going to revisit that quickly. A lot of the processes that occur in our bodies and around us are at equilibrium. Now, equilibrium, when we saw it in the previous chapter, is a process in which the rate of the forward reaction is equal to the rate of the reverse reaction. Now, this is a balance point, and this does not mean balanced in terms of the amounts of reactants or products. It means a balance in terms of the rate. The rate, for example, at which carbon dioxide flows into your bloodstream is going to be equal to the rate at which this bicarbonate is also coming out of your bloodstream. So, doesn't mean it's the same amount. It means that the rates are going to be the same. In order to have equilibrium, we have to have the reactants and the products in contact with each other. Otherwise, one of them can simply, evaporate off or react out. But in this case, if we have bromine as a liquid in contact with bromine as a gas, and we have it in a sealed container and we allow equilibrium to be reached, the rate of the forward is going to be equal to the rate of the reverse. Now, in the previous chapters, one of the things we would say about this is that our solution has to be saturated, meaning that no further reaction is going to be visible, that all that can be dissolved or all that can be, in this case, vaporized, is going to have occurred. So let's imagine that we have, and again, it's got to be sealed, in contact, and we've got water as a liquid evaporating and making water as a gas. Now, in order for this reaction to be in equilibrium, the rate at which it goes forward from going from a liquid to a gas has to be the same as the rate in which it goes from a gas into a liquid. And this is going to take time, and once we get there, we are going to be at equilibrium. So let's look at this reaction. First of all, there's going to be rules, and rule one is our reactions have got to be balanced. So if we have two SO3s going into SO2 plus O2, when we reach equilibrium, the rate at which the forward reaction occurs is going to be the rate at which the reverse reaction occurs. The equilibrium doesn't matter what we start with. We're going to have to reach equilibrium. So let's say that we start out here with no sulfur dioxide and no oxygen. So we have zero products. And we have lots of the SO3, the reactants, or the apparent reactants from this reaction. The SO3 is going to react, going to make SO2 and O2, and we're going to reach equilibrium. Now, equilibrium is going to be a point on this where things level off. And things are leveling off because otherwise we would not have the same rate in forward or reverse. The only way to make that occur is for our concentrations here to be level. Now, in this reaction, we have oxygen and we have SO2, but no SO3, which means we've got this stuff, but none of this. It doesn't matter. The SO2 is going to react with the O2 until we reach the same equilibrium point. It doesn't matter what you start with. The key for equilibrium is that the reaction is going to occur until you get to equilibrium. So, from kinetics with our little k, we know that if we have the reaction A plus 2B going in a forward direction to AB2, and in the reverse, AB2 is going to react to go back into the reactant. And we have the two reactants that we write directly, our rates directly from our balanced equation. So the rate forward is going to be the little k multiplied by the concentrations of the reactant. The rate reverse is going to be the little k of the reverse reaction multiplied by the products or the concentrations of the products. At equilibrium, these two rates are the same. Well, if this is the case, we are going to have rate forward, KFAB squared is equal to rate reverse, KR, multiplied by AB, and we are going to generate ourselves a new constant. Now, the new constant here we're going to get because we're going to take and we're going to write the concentration of the products over the concentration of the reactants, and that's going to be equal to the ratio of the Ks. Those are our nice little Ks from our kinetics. So note our product here is AB2, so it's going to be on the top. The reactants are A times B squared, And the value of the ratio is going to be the ratio of the small k's. We're just going to rewrite this and call this big K. Our big K is the equilibrium constant. And the equilibrium constant says that if we allow a reaction to go to equilibrium, the ratio of the concentration of the products over the concentration of the reactants is going to equal some value K. Now note, because little k's depend on temperature, so does big K. So if we have an equilibrium constant, this is going to depend on both the reaction and the temperature. And you're going to find yourself in a lot of these cases, given the temperature as well, we're going to actually ignore it because it's just a number, but it will vary as the temperature varies. The ratio of the products of the reactants is a constant, and we get this ratio from our balanced reaction. So we call this, by the way, the law of mass action. The law of mass action simply says that if we have a reaction at equilibrium, the ratio of the concentrations of the products raised to their stoichiometric coefficients divided by the ratio by the concentration of the reactant, so products over reactants, is going to equal a constant. Now note, if this ratio was 10 to 1, it tells us that we have 10 products for every one reactant, and we'd have more products. If the ratio was 1,000,000 to 1, we'd have a lot more products. So if we look at this, we can say that if our K is very large, we're going to have a lot of products, and we say that the equilibrium will lie to the right, and we will favor products. If instead of having this, we would have, say, 10 to the minus 6 to 1, or 1 over 10 to the 6th, this tells us that we have lots of reactants. And if K is very, very small, which is 10 to the minus 6, we say our reaction lies to the left and that we have lots more of reactants. So we can tell what our reaction is going to do by the physical size of K. So we have some rules on writing these. First of all, we're going to have two kinds of Ks. We're going to have a K sub C and a K sub P. K sub C means concentration, and it's always going to have units of molarity. K sub P, this is going to be pressure, and it's going to have units of ATM. Now, K is unitless, and I know that we don't tend to have things that are unitless, but I'm afraid we're going to get into the realm of unitless for a while. So anytime we have K, we don't worry about what the actual values are. It is going to be unitless in our reaction. Now, in order to do this, because this depends directly on the reaction that you write, getting the K depends on the balanced reaction. So what if it's not aqueous or it's not a gas? Well, if we have in this case, a liquid, or we have a solid, liquids and solids are not aqueous and they're not gases. And in fact, we simply leave them out of the expression for the equilibrium. Meaning if you have a solid or a liquid, so anytime you see an S or you see an L, you are simply going to replace it with a 1 in your equilibrium constant equation. So what does this mean? This means, for example, if we are taking the reaction CO2 reacting with carbon as a solid to make 2 carbon monoxides, in order for this reaction to occur, you have to have some C as a solid. Now, how far this reaction goes actually has no dependence whatsoever on how much of this solid we have. All that matters is the amount of our gases. So we're going to have rules. Rule 1 is going to be write the balanced reaction. Because if you haven't got a balanced reaction, you can't write the equilibrium expression. So you're going to write the balanced reaction. Second is you're going to write your equilibrium expression. So you're going to write the expression for K. Now we're going to say expression because it's not an equation kind of the way we know it, because it depends on every balanced reaction. If you change your reaction, you're going to change your quote expression for K. So in this case here, because we have CO2 as a gas plus C as a solid goes into 2CO as a gas, our expression is going to be our products, which is our carbon monoxide, raised to the stoichiometric coefficient, divide by the amount of carbon dioxide. Because this is a pure solid, we're going to replace it with a 1, and down here we're simply going to have a 1, and we're going to ignore it. We will look the value of K up, and we can solve for something. So we're going to write our balanced reaction, we're going to write our expression for K, which is this equation right here, and then we're going to solve for something. So let's write a few equilibrium expressions. So when we ask you for the equilibrium expression, we're just saying that, hey, your K is equal to something. So in these cases, these are mostly going to be aqueous, but we've got some gases in here. So for this reaction right here, we could write either K sub C or a K sub P. And this one above, we've got aqueous here, so this has to be a K sub C. This one here has only a gas in it, so this could be either as well. So for equation 1, for the sake of an example, I'm going to write a K sub C. And you know you've got a C if you've got units of concentration or molarity. Our K sub C is going to be the concentration of the products raised to their stoichiometric coefficient, so chlorine squared. We're going to leave water off because it's a liquid, divided by the amount of reactants, which is HCl, raised to the fourth, times oxygen. For reaction number 2, I'm going to write a K sub C as well, again, because I've got aqueous. And my K sub C for this is going to be ammonium multiplied by chloride divided by ammonia, which is a gas and would have to be a concentration, even though it's gas. It's either got to be a Kc or a Kp. It can't be both. And because HCN is a liquid, we're going to leave it out. Now for 3, I'm going to do a Kp. Now when we do K sub P's, we're going to do the pressure of each individual gas. And so we're going to say that K sub P is going to be the partial pressure of our gas in the product, which is CO2. Note, nickel is a solid, we're going to leave it off. And we call this partial pressure, we just write it as a big P. So we're going to say that K sub P is the partial pressure of CO2 divided by the partial pressure of CO. For equation number 4, it's kind of interesting and straightforward, and its K sub P would equal the partial pressure of CO2. We'd have to leave CaO and calcium carbonate off because they're pure solids.